for this. Okay. So good afternoon once again. So the most common, one of the most common logic circuit is the binary decoder circuit. Okay. Now, this is very common because all circuits will have this, especially if they have input devices. Like if you, no, output devices. Okay. Like for example, the screen of the small screen of a calculator or cell phone. Okay. This decodes because the output or the internal system of a binary device uses binary numbers, right? But when the output is computed or is produced, it cannot be presented in binary because humans don't understand binary numbers. So they have to be converted into decimal. So that's the main purpose of a binary decoder. Okay, it converts binary into decimal. No? So one of the most distinguishing characteristics of a decoder is it's on the binary side. The input side is binary. So no, the input to the circuit is a binary. The output is usually decimal. Okay, do you follow? Because people read decimal, not binary numbers. How is decoding done? Decoding is done by using an AND gate and a NOT gate on the input. For example, if you have four inputs and you want to decode it, for example, 1011. Okay, on the input side, you can put a NOT for every zero. Okay, for example, you have a zero here, so you have a straight connection, an inverted connection. There's a NOT, no, a straight connection, another straight connection. Use them as input to an AND gate, no, and it is used to decode. Okay, it is used to decode the particular value, which is 1011. Okay, do you follow? Now here's an example of a 3-bit binary decoder. It decodes numbers 0 to 7. Okay, for example, this is the truth table of a 3-input decoder. The inputs are A2, A1, A0. The first combination is not of A2, not of A1, and not of A0. So 0, 0, 0. So on the output, there will be 8 outputs, D0 to D7. Only one of which will be high at the time. Okay. Okay, for example, if the input is 0, 0, D0 is high. If the input is 0, 0, 1, D1 is high. If the input is D0, 0, is 0, 0, is 0, 1, 0, the output is D2 is high, and so on and so forth. To illustrate this further, let us create this in Cedar Logic. I really have created this already, no? But I'd like to create this circuit itself, no, so that you'll see the process. But the other circuits, I'm just going to demonstrate right away without having to create them from scratch because it takes a lot of time, okay? But you know how to create them already. So we are going to decode. So therefore, we have 3 inputs, no? Okay. What's in our A0 bang sa taas? Yes, A0. 3 lang, no? We are not going to use 4. 4 is too complex. Okay. So this is our A0. This is our A1. Let's spread this further apart. This will be our A3. Okay. And in the output side, we will have D0 to D7. Okay. Kaya na natin, no? How many do we have? 4, 5, 6, 7. We'll copy more. This will be our D0. Okay. which is this is our D0. This will be our D1. This will be our D2. I just copied and pasted now. Control C and Control V. Control V rather. It's D3. It's D4. This is a 3-bit decoder. D5. Hanggang 8 because you can count up to 7 because you can count up to from 0 to 7. No? If you have 3 bits. You already know that. No? Okay. Then we will have the inputs. Let's move this a little bit here. Baka mabusan tayo ng ano. We may run out of space. Now the problem with this, if you look at the circuit, no, use the actual sample, no, one input may be connected to 1, 2, 3, 4, up to 8 connections, no, and a connector can only give us 3 connections. So how do we go about that? We can use a combination of 4 connectors, okay, which will give us 9 connection points. So we'll have an excess of 1. Do you follow? Okay. Any questions so far? This is a 3-input decoder. I've uploaded this already to Dagler, no? Do you follow? So you can have them. So the first is a 0, 0, 0. If you look at that, no? 0, 0, 0. So for every 0, we'll have a NOT. Okay? Do you follow? That's how we do it. For every 0, we'll have a NOT. So we'll have a 3-input AND gate. Okay. Put it this here. So we'll need 3 inverters. There's a way pala to shoot. Just connect it right when the bar appears. No, it's already connected like that. No, it's already connected. No, when the bar appears. This is a big. Smaller. Okay, the bars when the bar appears is already connected. Okay, so, sorry, I think no, it's the square that appears. No. Yes. Sorry. You release the mouse when the square appears. Okay. Do you follow? Can you move it here? Closer. Let's see, we are going to connect it to D0 anyway. Okay, you follow? So we are going to connect it to D0. And now we need to make at most 8 connections. So for each of it is here. It will connect like that. We'll have to connect 3 more. We have to space it. No? So maganda mas malayo space so that we will have the lines will not stick to each other. No? So if we have that and we will connect this to that, no? Eventually we will have 9 connections available. Okay, 9 connections, 3, 6, 9 connections. Okay, we'll also do that here. Okay, do you follow? Move this a little bit down. Okay, we also do that here. We are doing this because we need 8, at most 8 connections. So, okay, that's why we have this. Okay, you follow? And then this one will connect to an A0. This one will connect to our A1. This one will connect to A A2. A2 pala ito, no? A2. Let's transfer this here, no? So that hindi masyadong ano. Okay, the circuits won't mess up so much. Okay, so this is 0, 0, 0. Take note, it's the 0 lights up because all of them are zeros. And then we will need a 0, 0, 1. Okay, so we'll decode each one for a 1. So since we have 0, 0, 1, we only need to connect to two NOT gates. Yan, okay. So this is 0, 0, 1. Every NOT gate stands for a 0. Connect it here. Ganun. The connection is extended. You just delete the connection first. You follow? It's okay now. So we'll connect this to A0. This one will connect to A1. This one will connect to A2. Do you follow? So for example, if you'll have a 1, no? A 1, sorry, no? A 1 is this, no? So that's 1. Okay. And if you close this, that's 0. We still don't have a 2. So we'll have to make a 2. A 2 is a 0, 1, 0. So we'll only need one AND gate. Not gate 0. No, we'll need to make 2. 0, 1, 0. And then we'll move it here, this there. Because we'll connect it here. This first one will connect to A0. Then we'll arrange. Second one will connect to A1. We'll arrange again. And this third one will connect to A2. Okay, do you follow? So do we now have a 2? Yes, 2. Okay, this is 1. Okay, that's 0. Do we have a 3? We have a 3. No, we don't have a 3. So we'll have to make a 3. This is the 3. So we are decoding its number, okay? Its value we are decoding using AND gates. So an AND gate is basically a decoder for the no. So the 3 is 0, 1, 1. So we only need one inverter. Make it there. No. So we'll connect this now to A1, A0. No? So we arrange. Okay. This one we connect to A1. That's okay now. This one we connect to A2. Okay, so do we now have a 3? Let's try that. That's a 3, no? That's a 1. That's a 0. That's a 2. Okay, do you follow? We need another AND gate for 4. 4 is 1, 0, 0. So therefore, we need 2 AND gates, NOT gates. Ito ang sinasabi ko ngayon, we're running out of space now. Let's move this here. D4, okay? 4 is 1, 0, 0. So therefore, we need 2 NOT gates. 0 on the first. We need another 0 on the second. And that's 1, okay? 1, 0, 0, 0. So we connect this to A of 0. It's okay. It's arranged. Ito lang konti. Okay. And then we connect this to A of 1. Okay, that's okay. And we connect this to A of 2. That's also okay. And we connect this to. Let's try a 4. 1, 0, 0. That's 4. Okay. That's 3. Okay. That's 2. That's 1. That's 0. Okay. Take note, no? The check colors will change according to one. And then we'll need a 5. Any questions so far? We need a 5. What's a 5? 1, 0, 1. Okay. Can we copy this? Yes. Ganun, pero hindi niya, it didn't copy the NOT gate. And ganda sana, no? Okay. 1, 0, 1. So we need a 0 in the middle. Okay. Then we connect this to D5. Okay. 1, we'll connect this to A0. Change a little bit. This one will connect to A1. Arrange this a little bit. This one will connect to A2. Okay. You follow? We have D5. This, what's 5? 1, 0, 1. Okay. They follow, that becomes 5. That becomes 4. That becomes 0. Okay. What's a 6? A 6 is 1, 1, 0. 1, 1, 0. Okay. 1, 1, 0. So we need one NOT gate. It made a wrong connection. So we need to re-input the output. Okay. So what's a 6? 1, 1, 0. So we need one inverter. Right? Yan, that connects it. Then we'll connect this to an A0. Arrange it a little bit. This is to A1. Okay, and this is to A2. A2. 6. So let's try 6. 1, 1. 6. They follow 1, 1, 0. That's a 6. So I hope you see the logic there. No, we are trying to decode what the binary number is. Okay, for 7 we need 1, 1, 1. So we don't need any NOT gate here. Okay, I'll connect it this here. This is the last connection anyway. Let's not make a big deal of this anymore. We follow? Let's try a 7. A 7 is 1, 1, 1. So that makes it a 7. Do you follow? So do you see the decoding process? Excuse me. So, excuse me a while. Okay, so this is a decoder. Okay, this comes, for example, in the output side, if this is a decimal display, no, or an LCD, or an 7-segment display, this is one that is sent to the output. Okay, any questions so far? Now let me open a file which is already there. No, by the way, no, basic logic circuits. It's already there in Dagler, which something which you can download. Okay, right away, no. So nandito sa Dagler. You can download, no? Okay, so this is this, the basic logic circuits in Sidor Logic. This is a zip file. You unzip, and excuse me, you will get this, no? Basic logic circuits. Let's open this. So on page 1, you have the decoder, which I have just shown you. Do you follow? Okay. Any questions so far? On page 2, you have the next uh, circuit. It's called encoder. Encoder is the opposite of decoder. Okay. So the encoder is used on the input side. No, that's because human input comes in decimal. Before it goes into the system, it must be converted into binary. No, so when people type their input to a computer or to a cell phone, they use decimal numbers, right? So they type 1, 2, 3, 4, and then before it's used by the system, it's converted into binary. An example. Questions? Questions? So anyway, an example of this is your computer keyboard or your keyboard from the from your calculator. No, when you press 1, it's converted into binary 1. When you press 2, it's converted into binary 2. Do you follow? When you press 3, it's converted into binary 3. Now what it uses, it uses the OR gate. Do you follow? Okay. Now to demonstrate how the encoding is used, let us open the corresponding CDR logic circuit. So this is the same circuit which is there. Now anyway, look at the first gate. No, 1, 2, 3, 4. We need a 6 input, or 1, 2, 3, 4, 5. We need a 5 input OR gate, but we don't have a 5 input OR gate. We only have a 4. Do you follow? So what we do is connect another OR gate to the input. So that will 1, 2, 3, 4. That will extend it by 1. So we will have two of these gates connected together. We'll make 5 input OR gates. Okay. So for example, if you have 2 OR gates connected in series, you will have a 3 input OR gate. Okay. So that's a technique when you run out of gates which requires larger input. Do you follow? So for example, on the keyboard, when you tap 0, so 0 ito. Do you follow? Okay, this is like the keyboard. Now when you tap 1, it's converted to 0, 0, 1. Do you follow? And then on your keyboard, when you tap 2, it's converted into 0, 0, 1, 0. That's binary 2. Okay. We recorded? Yes, no. Now when we tap 3, for example, we tap 3. You do not tap 2 keys at a time, right? Tap 3. So you have 1, 0, 0, 1, 1. That's binary 3. Okay. When you tap 4, 1, 0, 0. That's binary 4. When you tap 5, it's 1, 0, 1. When you tap 6, it's 1, 1, 0. When you tap 7, it's 1, 1, 1. When you tap 8, it's 1, 0, 0. When you tap 9, it's 1, 0, 0, 1. Do you follow? No? So that's an encoder. What's the difference between a decoder and an encoder? We'll have this in our test. In the decoder, the input is binary. In the encoder, the output is binary. The output is binary. Okay. So the next circuit is an enable switch. Now, an enable switch is like a faucet. If you have a programming language, if you're using a programming language, it's like an if then else. Y is equal to A if E is 1. If enable is 1, Y is equal to A. If enable is low, Y is equal to 0. Do you follow? Okay. Let's check that here. Yeah, I think it's at page 7. Mali na. Let me open. Kasi that was my sample circuit. Okay. Or that basic logic circuit CDL. I think it's in 5, no? Page 5, huh? No, 6. Enable switch. Look at this. This is our A2. No? This is the A. Then we have two variables, A and Y. Okay. A is 1101. So what is this? 4, 8, 1, 2, 1, 2, 4 plus, this is 11. But what happens to y? It's still 0. But when you enable, y becomes a. What's the technique? It uses an AND gate ANDed with enable. And this now ANDed to the input. Now when enable is low, anything ANDed with low will be 0. So therefore the output will be 0. Okay? When enable is high, anything ANDed with a high or 1 is itself. Therefore, A will go to Y. So it's like a faucet, no? In a water piping system, no? In a plumbing system, it's like a faucet. When you set the faucet on, water flows. If you set the faucet off, water stops. Okay? Water flow stops. Any questions so far? So that's an enable switch. Okay. Half adder. Okay. This is important. This is going to do, a half adder circuit is going to do 2-bit addition. Remember, no? In 2-bit addition, what is 0 plus 0? 0, carry 0. What is 0 plus 1? 1, carry 0. It will compute both carry and sum. What is 1 plus 0? 1, carry 0. What is 1 plus 1? 0, carry 1. So in the half adder, the sum is done by an XOR gate, and the carry is done by an AND gate. Do you follow? Okay. So let's look at our CIDR logic circuit. Half adder is in page 3. Pwede ba ito i-move? Hindi pwede, no? Okay. Half adder is in page 3. This is the sum and carry, okay? This will do 2-bit addition, no? In binary. So 0 plus 0 is 0, carry 0. 1 plus 0 is 1, carry 0. Okay? 0 plus 1 is 1, carry 0. Do you follow? 1 plus 1 is 0, carry 1. Do you follow? Okay? Any questions? So that's a half adder. It's a half adder because it adds 2 bits. A full adder is something which adds 3 bits. Because sometimes when you add numbers together, there will be a third input, which is the carry of the previous. Okay? So full adder, A, B, and C, or X, Y, and C. Now, the sum is actually okay, from C. Okay? The XOR of A, B, and C. Do you follow? Can we do a 3-bit XOR gate? I'm not sure, no, if we can have a 3-bit XOR, but this is the normal configuration. Even if you Google 2 XOR gates in series, no. Okay. Can we go to our now? Let me go to the CIDR logic. Okay. Full adder. Okay. Full adder. Okay. So 0 plus 1, 1 carry 0. 1 plus 1 plus 1, 0 carry 1. Do you follow? 1 plus 0, 1 carry 0. 1 plus 1 plus 1, that's 1 carry 1. Okay. So this does binary addition of 3 bits. Any questions so far? Okay. You have to remember this now. Familiarize these circuits. We'll use this in hardware. Now, the next piece of hardware we will have, circuit we will have is a piece of hardware. Adder subtractor. Now, it's like this, no? Each of these white boxes are full adders. We have X, Y, and C. Okay, C is the previous carry. To add 2 bits, the carry of the first adder is set as the third addend. The second addend, the third addend of the next adder. So the previous carry is the next addend. The previous carry is the next addend. The last carry is actually the last carry, our identifier whether the result is in negative or not, positive or negative. No? I have added this circuitry because sometimes during addition, you have to convert the sign into plus. When it's red, the sign is plus. When it's black, the sign is red. When it's black, the sign is negative. Okay, di ba? Ganun yun sa 2's complement. Okay. First, let's try 5 plus 2. A is 5, B is 2. Okay. For 5, you will have 0, 1, 0, 1. Okay. So 5 na kagad siya because B is currently 0. For 2, you will have B1 as high. Na? Okay. So 5 plus 2 is 7. 7 is 1, 1, 1. The last carry is a red, so this is a positive number. Okay. You follow? We will explain how the subtraction is done, no? In a short while. Now let's try 2 plus 7, 2 plus 5. Or you want 2 plus 7? Yes. 2 is 0, 1, 0. 7 is 0, 1, 1, 1. Okay? Tama ba ako? Kulang na yung isang 1 ito. 1. Okay? Okay? This is 1, 1, 1. That's 7. Okay, and 2 is 1, 0. Okay, so 2 plus 7 is 9. So this is 1, 0, 0, 1. That's 9. Do you follow? Do you follow? Okay, now let's try to do subtraction. Okay, let's try to do subtraction. When subtraction is high, this input S for subtract is high. Okay, when S is high, it will do a subtraction. When S is low, it will do an addition. That's why it's called an adder subtractor, or more commonly known as an arithmetic logic unit, or ALU. In this case, this is a 4-bit adder subtractor. Okay, do you follow? Any questions so far? Now, let's try to do subtraction. 5 minus 2. 5 is 0, 1, 0, 1. 2 is 0, 0, 1, 0. Let's do a subtract. Di ba 7 yan? When you do a subtract. So 5 minus 2 equals 1, 1, 1. 1, 1 is 3. And it's positive. Do you follow? Okay. 5 minus 2 is 3. Okay. Now let's do 2 minus 5. Let's do 2 minus 5. Okay. 2 is 0, 0, 1, 0. That's 2 for A. Do you follow? 5 is 0, 0, 1, 0, 1. So 2 minus 5 is negative 3. Take out this is black, no? So the result is in 2's complement. So this is in negative 3. 2 minus 5 is negative 3. Why? Because this is in 2's complement. The 1's complement of 3 is 1, 1, right? So the 1's complement is 1, 1, 0, 0 plus 1. So this is the 2's complement of 3, 1, 1, 0, 1. So in other words, 2 minus 5 is negative 3. Okay? Do you follow? You can test this yourself. Now you can download the circuit and test this. Now, in a normal adder subtractor, this part is not here, no? Because you can use this if you have an adder like this. You can use this to create bigger adders. For example, if you have a 4-bit adder, you can create a byte adder. You place 2 4-bit adders side by side and connect the input to the output in series. So you will you will get a bigger adder, which is now an 8-bit adder. If you have an 8-bit adder, can you make a word adder? A word is 16-bit. Yes. You put 2 byte adders and connect the output of one to the input of the other, the second, and you'll make a bigger adder. Okay, so this is now our first application, okay, of Boolean arithmetic in Boolean algebra, an adder subtractor, or otherwise known as an arithmetic logic unit. We'll go back to this a lot of more times, no, when we discuss hardware. I presume that you know how it works, no. Therefore, remember that that this white boxes FA XYS is same as this XYC. No, by the way, XYCI itong tawag niya because CO is the output. Do you follow? This is CO. Okay. This is CO. This is CI. Okay. So XYZ, XYC. That's there it is. Every one of this is it's called white boxing. Okay. You will have a white box, but you assume that you know that inside the box is this. Okay. Do you follow? Any questions so far? No. So full adder, adder subtractor. That's what it is. Digital latch, no? Digital latch is used for making memory. We'll not discuss this any further because this belongs to another. No? We'll discuss this in another. Let me discuss one more. No? There are actually many. Actually, in my other class, I have a lot more. Okay. Enable switch. Okay. Enable switch. Have I discussed this? Na-discuss ko na, no? It's like a faucet. This, the word comparator. Okay. What is a word comparator? It is actually part of an arithmetic logic unit. You add this to the ALU, you will have a comparator. This compares whether two words are equal or not. Do you follow? Now, this is done by comparing each bit of the two words. A0 is compared with B0, A1 is compared with B1, A2 is compared with B2, A3 is compared with B3. Do you follow? Now, how is comparison done? Comparison is done when you have an XNOR gate. Do you follow? Do you follow? So we'll say they're equal, no? Because 0, 0, 0 is equal to 0, 0, 0. How about if you click this on? Okay, they are now no longer equal. Do you follow? No? Do you follow? Now, if you look at each of the OR gates, you'll know specifically which violated the equation. The black output of an OR gate is the one which causes it to be unequal. And since they are used as input to an AND gate, anything ANDed with a 0 is a 0. So if you make this a 1 also, no? Now you know that they are unequal on the second and the third bits because this is our block, okay? They follow? So when you say put this here, one of them becomes equal. When you set this on now, all are equal. Okay? Any questions so far? Okay. So this will be our last topic for this session, no? For this session, because next meeting we will start with a new topic in hardware. Dito na tayo sa hardware na. Computer hardware, okay? Okay. So dito, no, we will be talking about a lot of the other circuits. Okay? And then when we finish this, okay, we will have our formative test number 3, no? Pagkatapos natin dito sa hardware and storage, computer storage, okay? Kano sa ang F3? Third week of October. Third to fourth week, okay? FT3, third week of October. Medyo malapit na, no? Because next week is October already. Next week is first week of October. You had your practice test already, right? Yes. Okay, let me check the attendance again, okay? Thank you for reminding me. No? CNTC. Yeah, I've checked you already. Aguelo. Ano may structure sa Aguelo? Angeles. Areza, are you there? Baka nandyan sa waiting room. Nobody's waiting there. Serbo. Serbo attends my morning class. But it's okay, no? You just tell me that you attend another class. It's the same set of sessions. Tell me before, no? Espinosa has been absent for a long while. Insigne, are you there? Iwata, Wookie. Paraiso. Si Paraiso. Paraiso. Pulido, wala. Okay, anyone else? Okay. So our third formative test will be on the third week of October. Okay. And then we'll have our we'll go to programming and software. Okay. This will be our last set of topics. I hope you have a 1 month here, no? 1 month tayo dito. The whole of November. Any questions? So after our third formative test, we'll start right away, and then we will have our summative test, no? Wala na tayong fourth formative test. We'll have our summative test right away after the okay? This will be on November already, no? Any questions so far? So we'll end up early today, no? We'll start with a new topic next meeting. We'll not introduce a new topic anymore. Any questions so far? So see you everyone. Class. See you next meeting. You review this, no? I don't like to introduce a new topic now with 30 minutes. No? So I'll record this and post this there, no? In our class. Thank you very much, no? No more attendance si Dagmil. Yeah, no? Okay. See you everyone. Thank you.
Thank you, sir.
Salamat, sir.
Thank you, sir.
Thank you,
Thank you,
sir.
sir.
Thank you.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.